Welcome to the lesson on controlling the process. Upon completion of this lesson, learners will be able to identify several benefits of process control, explain different process control techniques, and discuss the various quality control systems. In manufacturing, a process is defined as the flow of goods from raw material to the finished product. With the recent industry focus on quality and lean production, it is necessary to take a more in-depth look at the processes upon which these two manufacturing characteristics depend. To understand the importance of production control, let us consider this situation. Imagine you are working in a manufacturing facility that assembles electric cars. As the finished cars roll off the line, you and a team of quality inspectors check the car to ensure everything functions, and some cars fail to pass the tests. These cars are disassembled, and much time is spent isolating the problem. What if the problem is a part of a supplier? What if a seemingly unimportant piece was manufactured the wrong size? Could the whole batch of pieces be out of tolerance? How many assembled cars will be affected by the same problem? These types of manufacturing process problems might arise if facilities do not have some form of process control in place. A process represents the flow of production steps that transform raw materials into finished products, while process control involves the careful regulation of various variables within these manufacturing steps. Process control data plays an important role in this system, as it consists of collected information that helps manufacturers track and monitor whether their manufacturing processes are meeting the product's specified requirements. Together, these three elements create an integrated approach to ensuring quality and consistency in manufacturing operations through systematic monitoring and adjustment of production variables. The benefits of process control can be categorized into three main areas: efficiency, safety, and reduced variability. In terms of efficiency, process control helps streamline manufacturing operations while ensuring the optimal use of both tangible and intangible resources. Safety benefits are particularly significant as process control makes safety a top priority by preventing hazards and enabling workers to identify unsafe conditions through continuous monitoring of operations. Additionally, it facilitates the early identification of harmful environmental conditions. Regarding reduced variability, process control plays a role in minimizing significant variations among products of the same type. This leads to improved product quality and increased cost-effectiveness in manufacturing operations. Monitoring a process is a critical part of process control. Many different methods can be employed to monitor a process. Companies may choose a method based on the product they are producing, the level of inspection necessary, or the production process used. The four methods used are observations, control limits, control loops, and product testing. Each of these will be discussed in detail in the following slides. Additionally, process control activities can be performed by humans, referred to as manual control systems or machines, and with no human intervention necessary, also known as automatic control systems. Ways to monitor processes may be both manual and automatic depending on the method. Observations are a commonly used monitoring method because they are one of the easiest to implement. Observation is a manual control system that requires an easily observable defect and an individual who knows how to identify a defective part. One benefit of having the operator inspect for defects is that by being familiar with the production process, they may be better able to identify the source of the issues. By seeing the defect firsthand, rather than hearing it from a third party, the operator would also be able to react quickly to prevent the defect from occurring or causing more damage. However, employing the operator as an inspector could potentially leave him or her with less time to run the production process. It is important to remember that identifying inferior products based on observation has a tendency to be subjective. This method may not be suited to products that require precisely accurate tolerances to be met or that carry a high degree of risk should the product be flawed. Control limits in process monitoring are statistically calculated boundaries, typically set at 3 standard deviations from the mean, that define the acceptable range of variation in a manufacturing process, with measurements outside these limits indicating that the process needs immediate investigation and corrective action. Process control theory states that mathematical control methods can be used to correct variances between those outputs that are desired and what is actually produced. Control limits use process statistics to identify products that have strayed too far from acceptable characteristic levels, such as size or composition. Standard deviation, which is the measure of how far something is from the average, is the most common statistical measure when setting engineering tolerances. In manufacturing, a tolerance is the amount of variation allowed in a product. Finished goods can be tested randomly or methodically to ensure they fall within the tolerances that establish a quality product. Control loops are the next type of process control method. There are two types of control loops: open loops and closed loops. In an open control loop system, process outputs are not compared to inputs. A closed loop, on the other hand, continually monitors and compares the output to the input and makes adjustments if the output is not what is expected. A closed control loop accomplishes this action by cycling through three stages: measure, evaluate, or compare, and then adjust. Here is a scenario that explains how a control loop works in automotive painting. In the paint thickness control system, a sensor continuously monitors the paint thickness on the car body surface, where the target thickness of 0.1 millimeters serves as the set point. When the sensor detects that the thickness has exceeded this predetermined set point, it sends a signal to adjust the paint application process. The paint thickness on the car body surface acts as the measured variable in the system, while the paint spray gun settings serve as the manipulated variables, including its flow rate, distance from the surface, and movement speed. These manipulated variables can be adjusted to maintain the desired paint thickness. This closed-loop control system operates continuously throughout the painting process, ensuring consistent paint application and quality across the entire vehicle's surface, much like how a water level control system maintains optimal water levels in a tank. The last process control method we will discuss is product testing. To understand product testing, let us revisit the fictional automobile factory example. The products were tested for performance and quality only after they had been completely assembled. As you might imagine, waiting until the last step to test such a complex product is an inefficient method of ensuring product quality. This is not to show that product testing is ineffective, but simply that it should take place at multiple stages throughout the production and assembly process. Hence, product testing is evaluating the performance of a product after each stage or at the end of the entire production process. Quality is defined as the lack of manufacturing defects in a product and is seen as the degree to which a product or service achieves previously defined attributes. The International Organization for Standardization, abbreviated as ISO, defines quality as the degree to which a set of inherent characteristics fulfills requirements. These attributes are defined either by the customer, by the design engineers, or by both. For example, in a car, the design engineers provide specific requirements for the diameter and thickness of its brake rotors. If they do not meet these specifications, the steering wheel may shake. On the other hand, if the customer tests the car and notices that there are not enough cup holders, the customer's perception of the quality is poor. However, for the design engineers, this number of cup holders meets the requirements. The quality of the product needs to be updated regularly in order to satisfy the changing perception of the customers and stay competitive in the market. Hence, it is important that the quality process ensures that the product meets the customer's requirements and is up to date with market trends. Now, let us look at some of the quality control systems in manufacturing. The theory of total quality management, or TQM, is one of the earliest theories regarding quality control. Unlike some of the other approaches that have emerged in more recent years, TQM is not centered on quantitative data. Instead, it is a series of long-term improvement practices with the goal of increasing customer satisfaction. According to the American Society for Quality, there are 8 principal elements of TQM. At its core, TQM is customer-focused, ensuring that all activities align with meeting customer needs. It requires total employee involvement, encouraging participation from all levels of the organization. The approach is process-centered, focusing on improving operational procedures and workflows. Cross-functionality appears twice in the elements, emphasizing the importance of teams working across different departments and functions. Strategic planning provides direction and long-term objectives for quality initiatives. The system relies heavily on decision-making based on data analysis rather than assumptions or intuition. Finally, effective communication throughout the organization ensures that quality goals and initiatives are clearly understood and implemented by all stakeholders. As the name implies, statistical control is a theory based on quantitative process data and statistical analysis. This process is used to make sure the final product quality matches the product's requirements. There are two common terms associated with statistical control: statistical process control and statistical quality control. However, a distinction should be made between these terms. Statistical process control is the use of statistical data and quality control tools to monitor process inputs. This method can be viewed as a preventative approach, as processes are monitored to identify potentially defect-producing conditions before they occur. Statistical quality control is the use of statistical data and quality control tools to monitor process outputs. Because this method does not react until a defective product has been produced, it can be seen as a corrective method. There are 7 main control tools used in both statistical control methods. They are check sheets, control charts, graphs, histograms, Pareto charts, scatter plots, cause and effect or fishbone diagrams. 5S focuses on maintaining or improving quality through organization rather than data. By organizing the workplace around the production area, you can reduce variability and risk. The name 5S originated from the 5 steps of the methodology, each beginning with the letter S in the original Japanese and later translated to English. Each step of the method is built on the one before it, thus providing a structure for implementation. The first S involves sort, which focuses on removing all unnecessary tools and items from the workspace. The second S, set in order, ensures that every tool and item has its designated location within the workspace. Shine, the third S, emphasizes keeping the workspace clean and orderly. The fourth S, standardize, requires that similar workstations maintain consistent organization patterns and establish regular cleaning and organization schedules. Finally, sustain, the fifth S, focuses on maintaining these principles over time through consistent application and monitoring. Together, these 5 principles create an efficient, organized, and productive work environment. In summary, process control improves efficiency, safety, and reliability while reducing defects. It refers to the flow of goods from raw material to finished product, ensuring that each step of production meets quality standards. Process control can be either manual or automated, using methods such as observations, control limits, control loops, and product testing to monitor and improve processes. Key quality control theories in manufacturing, such as total quality management, statistical control, and the 5S methodology, provide structured approaches to maintaining high-quality standards throughout production. Thank you.